I suppose it's math time for only a few more times, though. Technically, there's 5 classes left, but I want to give you time to work on the projects and ask me questions and stuff, so it'll probably be 3 lectures and then 2, like it was last time, where you get to work on stuff and ask me questions and whatnot. So, roughly 3 more days of math, which is, yeah, you don't cry too much. So, because I want to hopefully stick to that schedule and give you the reduced math lecturing, let's get straight into it. So last class, I wanted to start the topic of matrices and why we would care about them and whatnot. And it was a lighter topic than what we talked about the day before. So I'm just going to quickly review that. So a matrix is just a grid of numbers, right? We call it n by m. This is 3 by 3, so the number of rows by the number of columns. To these matrices, we can do a few things, which we call row operations. We could swap 2 rows around, so we could swap these 2. We can multiply one of the rows by a non-zero number. So, you could multiply it by 2 or divide it by 2 or whatever you want. And then you can add a multiple of one row to another. And this one doesn't say add a non-zero multiple because, there's nothing stopping you from going add 0 times row 2 to row 3, but you didn't do anything. So we don't need to specify non-zero because if you do a 0 multiple, nothing happens. So it's fine. But those are the 3 row operations that we can do that we're really interested in. And I finished off with what we call the row echelon form of a matrix, which just sort of has this staircase shape, right? Where if you pick a row and go to the leftmost non-zero thing, all below it is zeros, right? And then that will give you something that has that shape. We also had what I call the augmented matrix. So the notation we use looks like this. And it's just the numbers that go in this left side before the line are all the things on the left side of the equal sign of an equation, so all those numbers. And the right side is just what's on the right side of the equal sign. So it's relatively easy to do, and we're going to do a lot today, so that's why I didn't write it here, because we're going to talk about how we can solve systems of equations using this technique. But we're going to need a couple of definitions and some practice here. So this is a definition. So here we call this, the shape is called reduced or row echelon form, but a matrix has a concept of being in row echelon form. So a row echelon form is exactly what you'd expect it to be of a matrix A is something that looks like this, of the form given for row echelon form. So this is just distinguishing between hey, this is just a shape that we can talk about. This is saying we're going to say a matrix is in row echelon form or has a row echelon form if we can make it look like this. So row reduction is the process of using row operations so these things to bring a matrix to a row echelon form. So what we're saying is we can do these steps to turn something that looks like this, any matrix, into something that has a staircase shape. So, okay, what's the process here? it's not going to be that surprising, right? It's kind of what you would expect it to be. So first, find essentially a row where the leftmost entry is not 0, right? So like any of these would work, right? Because the furthest left entry is 1, 4, or 7 for row 1, 2, and 3. So pick one. Doesn't matter. Usually you pick the top one, but if the top left spot is a 0, then you're going to switch it with something that isn't. So find the leftmost column. That is not all zeros. Let's say move the non-zero entry to the top. So that would probably mean swapping it if it's not already 0 at the top. Top left, let's say. Now, what that means is we have a non-zero entry at the top left. So now we can add a multiple of this row or subtract a multiple of this row to everything below it to make zeros below it, right? Because think about this shape. We want this top left entry to have zeros all below it, right? So we can just do that. Use this entry to create zeros below it. Okay, so then we would have something that looks sort of like this, right? Now we basically just cover up the row and column we just dealt with and repeat, right? So we might need to swap some rows and then we just do the same thing. Cover up. Mentally, you don't actually have to do that. The row we just used. And repeat this process. So it ends up being very methodical. Just kind of go through the motions. So again, this is another one of those situations where putting it in words makes it sound worse than it is. When we actually do it, you'll be like, okay, yeah, it's most of the stuff in linear algebra involves adding and subtracting and multiplying small numbers to each other, right? And it's easy to mess that up in the sense of arithmetic mistakes are easy to make, but conceptually, it's not too hard. So, okay, let's consider, we're going to do an example of this. Matrix. So it's going to look like this. 4 minus 2, 3, 2 minus 2, 2, minus 3, 8, minus 12. So it's just a nice looking matrix. So what we're going to do is we're going to perform this process on it to reduce it to a row echelon form, right? So something that has that staircase shape. So there's a couple of things you can do here. When it comes to these types of problems, so if I present you one of these on an assignment or something like that, I always construct it so that there is a path that lets you avoid fractions. Did you choose that path? Well, I don't know. I can't tell you what to do because the goal here is put a non-zero number at the top left and use it to make zeros below it. All three of these are non-zero. So you could pick any one of them, right? So you see you already have a choice. All of them will lead you to the same answer. It's just some of them will have horrible fractions. But I will always make it so that there is one path that does not. And also your final answer, other than like one or two exceptions on the board, shouldn't have fractions in it either. Because I'm not here to test your ability to add fractions. I don't care if you can do that. I'm here to test, going through these motions. So if you got fractions at the end, you should probably be like, Travis, I think I screwed it up. Or I screwed it up, right? If everyone's getting fractions, then I'd be like, uh-oh. So this is a perfect example of this, because generally speaking, if we want to create zeros below it, it's best if this top left number is a 1, right? Because then it's easy to just multiply it by 2, subtract 2 times it, and then add 3 times it to this, and that will create zeros, right? So we want this ideally to be a 1. Let me just add a little note here. Ideally 1. So sure, right here we could divide by 4, right? First row by 4, then we got a 1 there. But now we have a -1/2 and a 3/4. That's kind of bad. So if I look at this though, the second row, if I divide that by 2, it becomes 1 - 1, 1. So that creates a 1 there without fractions. So let's do that. So let's swap row 1 with row 2. That seems like a good choice. So 2 - 2, 2. 4 - 2, 3. -3, 8, -12. And now we're going to go ahead and do what we said. We're going to divide row 1 by 2. So this is going to be 1 - 1, 1. And we didn't touch the others. 8 - 12, like that. Now, you can combine a lot of steps here to save yourself writing down the same matrix over and over again. You're going to see very quickly that one of the quote-unquote challenges of these problems is it's going to take up the whole board, right? It's just a lot of writing. So if you can save yourself that, I encourage it. So in this case, as an example, what we want to do now is we grab this entry. We want to make zeros below it. So that's going to be row 2 becomes row 2 minus 4 row 1. But then we can also just deal with the third row at the same time, right? So row 3 will become row 3 plus 3 row 1. And we can just do it at the same time. Nothing stopping us from doing that. Okay, so we're gonna go ahead and do that. So our first row, we didn't change it. So this we know, I don't even need to calculate it. I know those are zeros. I made it so that they are zeros, right? So now we have to deal with the other pieces though. So this is row 2 minus 4 row 1. So -2 minus 4 times -1. So -2 plus 4 is 2. 3 minus 4 times 1 is -4. 3 minus 4 is -1. 8 plus -3 is 5. And right here, so 3 times 3 added to that gives us 9. So that's 3. Did I do that right? I did. Oh, wait. Hold on. I think I screwed up the numbers already, which is funny. I didn't. Well, I wrote down the question wrong from what's in my notes, but we can still fix it. It's fine. We'll do it. Because this actually lets me show you another thing. So we look at this and we're like, hey, wait a minute. If we tried to divide by 2, we get a fraction there. If we try to divide by 5, we get a fraction there. So what could we possibly do? Now, I try to avoid questions like these because they're just a little tricky. But what we could do is if we subtract 2 times this from this, it makes a 1, right? So row 3 is going to become row 3 minus 2 row 2. So sometimes this happens, and like, again, if you just divided by 2 here and you said, screw it, I'm just going to do the fractions, right? You'll get the same answer. It's fine. You can do that. But we can also avoid them. So this is 2 times -2 added to this becomes 1, right? 5 minus 2 times 2 is -4, so 5 minus 4 is 1. 3 minus 2 times -1, 3 plus 2 is 5. Right, now we can put that 1 there. 2, swap it with row 3. One, 5, 0, 2, minus 1. And now we're in our golden position where we got a 1 here now, right? And then we just rinse and repeat, right? Because what we're doing here, we accomplished our goal in this step, right? We got a 1 here and all zeros below it. And then we see here it says cover up the row we just used and repeat. So that's why we're doing this, right? We cover that up. We want a 1 in the top leftmost spot that we can get to, which is here, right? Because we can't put a 1 there because they're all zeros. And then we just repeat. So now row 3 is going to become row 3 minus 2 row 1, or row 2, sorry. Numbers hard. 0, 1, 5, 0. This is a 0. We know it is. We designed it to be that way because we just did minus 2 times this to that. But now it's minus 1 minus 2 times 5 is minus 10. Minus 1 minus 10 is minus 11. And now we have this nice staircase shape, right? And so at this point, we would be done finding the row echelon form. So this is row echelon form. And we say we avoided the fractions. Now, if you want, if you don't believe me, if you instead divide by 2 here and do the same thing, you'll get the same shape. This number will be a little different, but we're allowed to multiply a row by whatever we want, so they're the same thing. So now you can kind of see this process, right? You know, when you watch me do it and you stare at like a grid of numbers, it just kind of washes over you and your eyes glaze over. But nothing here, none of the mechanical processes I did here were really out there, right? I swapped some rows around and I added some stuff to some other stuff, right? It's relatively simple math, which is what's funny because it's so easy to screw this up. So you'll notice I didn't look at this at all, and that's on purpose because at some point I will make an arithmetic mistake. And to me, it's important to show you that I've been doing this for like 20 years and I make them all the time. So like you should not be super upset at yourself or stressed over making them too, because they just happen, right? Like just think of, you know, this step right here. Minus 2 minus 4 times minus 1. Doing that in your head is like, which is why you can do it on your calculator if you want, or you can just write it on the side, right? So we know that this number, so right here, minus 2 minus 4 times minus 1. And you just write it on the side, and it comes. You can do whatever simplifications you need. Minus 2, you know, this is going to be plus 4 equals 2, right? So it can help to just write it on the side. If you're trying to do it in your head and you're like, I'm overwhelmed, I'm making too many mistakes, just write it down. It's fine. Nobody is going to, well, they shouldn't because nobody's perfect. If you do that and someone's like, why are you doing that? Just do it in your head. You could just say, I don't want to screw it up. Right? It's a homework assignment. I don't want to make a mistake and then lose marks because I was too lazy to write it down. But also, if you're confident, you can do it in your head too. That's fine. But this is, what we just did here is basically the meat of what we're talking about. It's just doing this stuff over and over and over again. So, how is this useful for solving equations? Well, suppose instead that this matrix here started as this. Now remember, this represents a system of equations, right? So if we first said this is step 1 and then this, that means every single one of these matrices represents a system of equations. And it's the same system of equations, right? These steps are all totally fine and we can do them to equations. So this thing means the same thing as this. We've just simplified it. Right? So you can kind of see how that would be helpful. This gives us a way to simplify basically the messy equations with all the variables and all that ugly stuff into something that's nicer looking, right? This is just doing arithmetic. We don't have any variables until the very end and at the very start. So because this matrix represents a system of equations, at every step of this row reduction. So that means at the very end here, you could do all the simplification and then say, okay, that's my system now. And then you just solve it, right? So we can do one better though, because if we're saying that, if we're saying, hey, this represents equations, right? Then so does this. So what does this look like as a system of equations? Well, we just go backwards, right? This would be our x variable, our y variable, and this would be the answer variable, right? So we would have x minus y equals 1 as an example, and we would have y equals 5. So then you could just sort of, do that. Now we're at the kind of messy part of our algebra here, where we would say, okay, y equals 5, now plug it in and go backwards, right? And actually, technically, this example is kind of bad because we also have that row, which is saying that there's no solution, right? But the point is we can reinterpret it as a system, right? And we can do the technique we already did. But we want to do a little better than that. Because what's really happening here, we're plugging this in, but what that ends up boiling down to is adding this row to this row. So we can improve this process. Once we get down to here, we now go from the bottom up and add multiples of the bottom right thing upwards. Right? And that will turn this into a 0, and this will turn this into a 0, and this into a 0, and so on and so forth, right? So we can improve this process. With what's called a reduced row echelon form. So it's the same kind of thing. That's why we're calling it a reduced version of something we already talked about. Because it looks the same, so it has that nice staircase looking shape, but it has one extra property. So a reduced row echelon form, actually it is the reduced row echelon form, of a matrix is, well, first, is in row echelon form. So I'm just going to say in brackets staircase, right? It's that same kind of shape. But now we have an additional condition, which, how do I write it down here? I want to make sure I am consistent. So that these numbers here, which we call leading entries, now they can't just be anything non-zero, they have to be 1. Right? We're insisting that they're 1. So right here we see, well, this is minus 11. We need to change that to be a 1 for it to count. So all of the leading entries the leftmost non-zero number in a row must be 1. And we can always do that, right? Because we can multiply or divide these rows by anything we want. So we can just always guarantee that that thing's a 1 at the very end, right? We just divide by whatever number we need. And the last thing is each column containing a 1 or a leading 1, so one of these entries, has zeros below and above. So if we look at this example right here, we're not in this form, right? Because this thing is not 1, and above it is not zeros. So how do we do that? I'm going to rewrite this matrix, by the way, because I need it. We can continue our previous process to get to this form too. So we ended off here. I'm going to draw an arrow going from the left because we did something to get here. 1 minus 1, 1, 0, 1, 5, 0, 0, minus 11, right? So now we can basically just sort of reverse our steps, right? Now instead of starting from the top left, we're going to start from the bottom right now that we've gotten to this nice staircase shape. And we just say, okay, make this a 1, right? This bottom right entry. So row 3 divided by minus 11. What does that give us? 0, 1, 5, 0, 0, 1. And we designed that to be 1. And now we create zeros above that thing we just touched. So that's going to be row 2. We're going to take away 5 times row 3. And row 1 is just take away 1 copy of row 3. We're subtracting 5 times this from this, and we're subtracting 1 times that from that. 0, 0, 1, 0, 0, 0, 1. And now we do the same thing, but just in reverse, right? We go from the top left down to here, and now we're going to go from the bottom right and kill stuff up. So we cover this one up, and then repeat. Or, well, I guess I've covered the row. So now we look for the bottom rightmost thing, make it a 1, and then kill it that way. So this right here, row 1 becomes row 1 plus row 2, because we want to turn that into a 0. And what do we get? We get something that looks very, very simple. Right? It has got that nice staircase shape that we originally started with. All of the leftmost non-zero numbers in a row are 1. And every single one of those that has a 1 in them is 0 above and below. Right? So this is a very simple looking form for something. So I'll write down this process in words. So this improved process bring it to row echelon form. Perform a similar process, but start at the bottom right. So that means pick the leftmost row that has a non-zero entry. Leftmost non-zero entry in a row at the bottom. So in this case, there, make it 1. And that's easy to do. You just divide by whatever that number is. And then use that to make zeros above. So add, subtract multiples of this to make zeros above. Then cover up that row and repeat. So again, it's another very methodical process. Technically, you can also do it, you could do both at the same time. So a sort of, I don't want to necessarily call it improved, is you could, as you're going through, create zeros below and above at the same time. But that might end up, you might not have a 1 there at that exact moment in time. So I would encourage you to go top left to bottom right and then reverse the process, because that might also get you some nasty looking fractions. Okay, so let's just do another example, because again, this is something that you're just going to need to be exposed to a lot in order to get comfortable with it. And yes, I will make you do some yourself. But not until I do a bunch. Actually, because I need space. Am I okay to erase this matrix, or do you need a minute? Okay. Because it's just going to take up space. So I would like to recover that space. Okay. So put the following matrix into reduced row echelon form. And this is the one that we're going to care about. In fact, we talk about it so much that eventually I'll just say RREF, reduced row echelon form. Okay, so we've got this matrix, and I'm going to be extra careful this time because I need it to be exactly this matrix. 2 minus 4, 2, 4, 5, minus 1, minus 1, minus 2, 1, 4. Okay, so we just follow this process, right? The first bit of the process is we're creating zeros below, right? So that hasn't changed yet. So step 1, we want to put a 1 at the top left. And like I said, there's multiple ways to do that, and you pick. So personally, I look at this and I'm like, I'm just going to divide this first row by 2 because that gives me no fractions. You also could take this and swap it with the first row and then turn the minus 1 into a 1, and that would also work. You'll get the same answer either way. But I'm going to do it this way because it's staring right in front of me. So row 1 divided by 2. So what does that give me? 1, 2, 1, minus 2, 2, 4, 5, minus 1, 2, 1, 4. Right, we just divided that first row by 2. And why did we do that? So that we can kill the entries below. Right, so these are going to become 0. So row 2 will become row 2 minus 2 row 1. Right, just whatever turns this into a 0 from that. We want to turn this into a 0, so row 3 will become row 3 plus row 1. Get rid of that. So we didn't touch this first row. We know these are zeros. We did that on purpose, so now we just need to figure out the rest of the entries. So we're doing minus 2 times this to this. So 4 minus 2 times 2 is minus 4. 4 minus 4 is 0. 5 minus 2 times 1 is 5 minus 2, so that's 3. Minus 1, and this is another example. I'm going to write it on the side. so that nobody, so you can see you can do it, minus 2 times minus 2. So that's minus 1 plus 4 is 3. Go ahead and write 3 there. Okay, what about here? We have to do this row now. Well, we're just adding these numbers. So minus 2 plus 2 is 0. This is 1 plus 1 is 2. Minus 2 plus 4 is 2. Now we cover up this row we just dealt with and repeat, right? So we take one of these and make a 1 at the top left. Well, it doesn't matter. Either of them will work. So I'm just going to be lazy and say row 2 divided by 3. And we're going to divide that by 3. Zero, 0, 1, 1. We didn't touch this one. Okay, well, now we know what to do here. We're going to do this row. We're going to take minus 2 of that from this. So row 3 is going to become row 3 minus 2 row 2. 1, 2, 1, minus 2. We didn't change that row. Didn't change this one either. Those were already zeros, so nothing's going to happen to them. So 2 minus 2 times 1 is 2 minus 2. We'll get 0. Same exact thing here. And we got 0. All right. So that is the process of putting it into row echelon form, right? That staircase shape. We got zeros all below. So there's only one extra step here, really. And it's we need to go through the rows, pick the leftmost non-zero entry in a row from the bottom. So the first row here on the bottom is zeros, so we ignore it. Here, leftmost entry, that's a 1 right there. And then we make it a 1. It's already a 1, all right, convenient. Now we add or subtract multiples of this to make zeros above. So we want to make a 0 there. So that means row 1 is going to become row 1 minus row 2. We're going to subtract this thing from this to make a 0 up there. 1, 2, these don't change because that's 0. We know that's a 0. We're taking this minus that, so minus 3. And now we've got that nice staircase shape. We've got these, the leftmost ones, zeros above and below. So this is what's called the RREF of a matrix. And it is unique. That's why I started the conversation with the row echelon, reduced row echelon form. Now, why does that matter? Well, this form here, there's lots of different ways to do that, and your answers might look slightly different from your friend, right? You got a staircase shape and your numbers are different. This, though, you will always have the same thing. So if you have different answers, at least one of you did it incorrectly. The reduced row echelon form is unique. So that is good for comparing answers, because you can just say, like, did I get the same thing? And lightning probably didn't strike twice, so if you both had the same thing, you probably did it right. So I'll make that remark. RREF, this shape we just found, is unique. But now, why would we care about this? So this is even better for solving systems. So why would I say that? Well, we're going to do more examples of this application, but let's say we set out to solve, let's say example. So it'd be 2x plus 4y plus 2z equals minus 4. 2x plus 4y plus 5z equals -1, and minus x minus 2y plus z equals 4. Okay, let's say we want to solve this. This matrix is that augmented matrix of this system of equations, right? The coefficients there, 2, 4, 2, 2, 4, 5, -1, -2, 1. Then we draw that bar, and the stuff on the other side of the equal sign, -4, -1, 4, right? So this is that system of equations. So we put this into that matrix. Two, 4, 5, -1, -1, -2, 1, 4. And then steps. We already did all these steps right here, right? So we're going to go ahead and perform those steps to get to here. 0, 0, 1, 1. Like that. But my point was, all of these steps along the way, at any point we could stop looking at it as a matrix and go back to these equations at any point. So, we could have stopped here and went back to equations again if we wanted to. But if we go back to here, what do we get? Hopefully I have enough space to write this. This number is what goes into x, or in front of x in the first equation. This is what goes in front of y. Can't write. This is what goes in front of z, so 0, nothing. Equals -3. 0x plus 0y, z equals 1, and that's it. So z is 1. Here we have something that we'll need to talk about. We have what's called a free variable here, but what that means is we're free to choose one of these. Right? We can pick x to be whatever number we want, and once we pick x, it tells us what y has to be. Alternatively, if you pick y, it tells us what x has to be. But z has to be 1. Right? We have concluded it's 1. So this process here skips all that equation solving nonsense. Right? At this point, we're done. Right? This is the solution. I mean, you would pick one of them and move it to the other side and say, hey, you can pick y to be whatever you want. But then that tells you x and z. So that's why we care about this, is it gives us a way to solve these equations. So going through this process, it has a name, it doesn't really matter. It is called Gauss-Jordan elimination, because Gauss is a mathematician who discovered a technique. It's in my notes. I'm not going to talk about it, though, because it's just this but worse. He discovered that technique, and then a mathematician named Jordan came along and said, hey, I can make this better. And so then that's why it's called Gauss-Jordan elimination. But the meat of it is, write your system of equations as a matrix. So that's this thing, right? Step 2, perform row operations to get to the, it's unique, reduced row echelon form. So the thing that looks like this. Now, reinterpret it as a system of equations and clean up. Print as a system and clean up. I'll show you what I mean by that. This is an example here where we have to sort of move one of the variables over and say, okay, you can pick it to be whatever you want. But sometimes we don't have to do anything. We just reinterpret it as a system of equations. It'll just be like, oh, x is 1, y is 2, and z is -1. I'm done, right? Now, the other reason why you can probably see this is interesting is it doesn't really matter what I write on the board. The process is the same, right? I'm going to make something, 1 at the top left, make zeros below it, close it off, repeat, right? And then I reverse it from the bottom right, which is very suited for an algorithm. Now, when we're talking about computers, though, there are actually more stable ways to solve systems of equations than this method because, if your computer doesn't care about fractions, well, it does, but in the sense of it's not going to struggle to add fractions to other fractions like we do. But there is a problem with adding fractions to other fractions in computers. Does anyone know what the problem would be there? Like, why can't we just, well, we can, but what's the problem in a computer of just doing this and just taking the top left one and just dividing by whatever it is and saying, screw it, the computer can figure it out? So the problem with that is rounding error, right? So if you had something that looked like this, 1 0 0 0 0 0 0 0 0 0, and this was 2, right? I mean, you need more zeros than this, but like something like this can happen. If you divide this by that, it'll become 1. Your computer will know how to do that. But then when it does this, you have a floating point number, which could have rounding error, right? And now you're adding and subtracting and multiplying these really, really small numbers to each other, and you can run into some problems. But for our purposes, it works good enough, right? You'd have to be dealing with very large data sets and very large numbers to run into that problem. But like as far as just doing the algorithm, it works pretty good. So let's just do a bunch of examples about it. Because there's really actually 3 situations that come up when we're talking about systems of equations. Because early on we mentioned that if you have a system of equations, there's 3 situations. Either there's one solution, no solutions, or infinite solutions, right? So what do these all look like in this algorithm? You can actually spot them pretty easily. So actually, we did this a couple days ago. Yeah, this one. So this, I'm going to say, is the exception. Example. Solve the following system. Using row reduction. So I'm going to say that instead of saying using Gauss-Jordan elimination, because that makes me feel like a wiener if I say use Gauss-Jordan elimination. No, it's this. It's what we just did, right? So the system looks like this. 2x1 plus 2x3 equals 0. x1 minus x2 equals 1. 3x2 minus 2x3 equals -1. So I try to write them down like this so that there's sort of gaps where the missing variables are, so that it's kind of easy to just look at it. But if you're more comfortable with it, you can actually fill this in with the zeros so that it's easier to read. 0x3, 0x1. There's just zeros there. Where there's a blank, you put a 0. So how do we do this? Step 1, write it as this matrix. That's what we do. So we're going to write this. So we just read this off. 2, 0, 2, slash 0, 1, minus 1, 0, 1, 0, 3, minus 2, minus 1. So this is, I think, the one exception in my notes. We will get fractions here. It's because the one we did that was where I demonstrated, hey, this is really ugly, had fractions in it, and this is the exact same system of equations. So we're keeping the fractions. I'm going to make a note to fix that actually, so we don't have the fractions. But for now, we have the fractions. So the first goal is to put a 1 up there. Again, there's 2 paths here. What do I do in my notes? Because I'm going to do the opposite so that I can present both. So in my notes, I swap this row up to there because that makes sense, right? We already have a 1 there. Here, I'm going to divide this row by 2. So now we're deviating from the notes, so wish me luck. So we divided this first row by 2, so all of those become 1. We didn't touch these other ones, so they stay the same. Now what we're going to do is we're going to use this to create a 0 down there. And we don't have to do it here because it's already a 0 there, so that's nice. So we're going to subtract row 1 from row 2. Row 2 becomes row 2 minus row 1. Okay. So we didn't touch row 1. But this is a 0 now. So now we're going to do this subtracted from this. 0 subtracted from this is, it does nothing happen, so that's minus 1. Now we're going to subtract this from this. So 0 minus 1 is minus 1. And then we're going to subtract 0 from 1, so we get 1. All right, well, this is working out pretty well. And this stays the same. 3 minus 2 minus 1. Well, now it's pretty easy to create a 1 in the second row. Just multiply by minus 1. So row 2 times minus 1. 0, 1. Actually, hilariously, I would say that's also probably the most common mistake is you multiply this row by minus 1. So you go, okay, I write a 1, and then a 1 again. You just forget to multiply that by minus 1. So easy to make that mistake. Okay, now we're in good shape, right? Because we just say, all right, we already did this one, right? So now we're going to create zeros below this top left entry. So we're going to kill that 3. So row 3 becomes row 3 minus 3 row 2. Sorry, I ran out of space there. That's row 3 minus 3 row 2. I get on my knees here, I think. And maybe not. We didn't touch either of these rows. So this is the only row we need to change. That's 0. Because we're doing 3 minus 3. Now it's minus 2 minus 3 times 1, so minus 5. And then minus 1 minus 3 times 1 becomes 2. And now we see, this is kind of the telling point where you're like, okay, nothing I could do here could stop fractions now, right? Because we've got that nice staircase shape. So now we need to go backwards, right? We take the leftmost thing and make it a 1. I have to divide by minus 5. That's going to have to become a fraction, right? Nothing we can do there. So this is row 3 divided by minus 5. And now things are how they are. 0. I'm going to run out of space. These take up a lot of space. 0, 0, 1, and minus 2 over 5. But now, to simplify this, we only have one more step to do, right? We just created a 1 there, so we use it to create zeros above it, right? So that's going to be row 1 becomes row 1 minus row 3, and row 2 becomes row 2 minus row 3. So this is 1, 0, 0, 0, 1, 0, 0, 1. And now this is the part where it's like, okay, I try to avoid these. So the minus 2 over 5, we're subtracting this from this. So this is minus 3 over 5. You could just use your calculator if you wanted it, if this ever happened. And then minus this added to this, well, that's just 2 over 5. Okay, but now we've got this nice staircase shape. And for all of these numbers here, it's zeros above and below. So, okay. What does this say? We got to the RAF. We're done that. Step 3, reinterpret as a system, right? So that thing means a system of equations. Great. So we take a look at that, and it says x1, and then 0x2, 0x3 equals 2 over 5. x2 equals minus 3 over 5. And x3 equals minus 2 over 5. We're done. Because this tells us the answers, right? x1 is that number, x2 is that number, and x3 is that number. And if you look back, we did do this exact system of equations using the terrible method. We got this answer. So I think reflecting on that with all of the messy equations and manipulating and moving stuff around and substituting variables for other variables and all that, this is just adding numbers. At the very end, we did end up with a fraction, but it was literally the last step. Whereas in the other one, we ended up with fractions like halfway through, right? And it was quite messy. So this is one of the situations. This is where we have a unique solution, right? It just tells us those are the numbers. You're done, right? And so what's the answer? Nothing. You don't have to do anything. You just write that. You say, done. I'm done. There's your answer, right? So there is another situation that can come up. But I'm going to give, is this okay to erase? I don't see anyone shaking their heads. So it's going away because we're going to solve another system of equations. So this system looks like this. Minus 4x2 plus x3 plus 8x4. So now there's 4 variables. X1 plus 2x2 plus 3x3 plus 3x4 equals 4. But the process is still the same, right? Nothing here has changed. Step 1 is still going to be, we're going to go ahead and write down this matrix. All right, that's always step 1. If you get this far, you get like 2 out of 5 probably. Maybe an exaggeration, but I'm going to give you marks for this because there's 3 steps. One of them is very long, but this is an important step. So we just interpret this thing. So we just write it down to minus 4, 1, 8. Just go along the numbers. Except the last one has that bar in front of it. Minus 1, 2, 3, 3, and 4. All right, cool. So now we just do the process, right? We want to create a 1 at the top left. So in my opinion, swapping this is probably the right choice. So row 1, swap with row 2. So it's going to be minus 1, 2, 3, 3, 4, 2, minus 4, 1, 8, and minus 1. Okay, cool. Now we just multiply by minus 1, right? And this is sort of what I mean. You can do things in your head if you're very careful and confident. So in this case, I know I want to multiply this by minus 1. So you could also just do that at the same time and say minus row 2. I'm not doing that here because it gets confusing if you're not very careful. So I'm doing it every step of the way, but I'm saying that's okay. If you want to do that, go for it. But now we're going to do that here. We're going to say, okay, we're going to multiply that row we just swapped in there by minus 1. So that just puts a minus sign in front of everything that doesn't have 1 and vice versa. Pretty straightforward. 1, 8, minus 1. Okay, so now the next step is make a 0 below this. right? We put that 1 there on purpose. So row 2 becomes row 2 minus 2 row 1. So that first row doesn't change. Minus 4. And this is going to be a 0, right? Okay, so now we just need to deal with all the other entries. So minus 4 minus 2 times minus 2. So this is minus 4 plus 4 equals 0. We put a 0 there. Again, I'm just doing this to say, hey, go ahead and do that if you need to. It's fine. 1 minus 2 times minus 3 is 6, so this becomes a 7. 8 minus 2 times 3 is 6. So 8 plus 6 is 14. And then here, minus 1 minus 2 times minus 4. So this becomes 8 minus 1 plus 8 is 7, or minus 7. Right? So again, it can be kind of horrible to do it in your head. Making sure. Wait, this is a plus. Yep. See what I mean? It's so easy. So easy to just do that. But point is, now we're okay. So we repeat the process, right? We can cover up that top row, which is long, but we just cover it up. Repeat the process. I'm just going to divide this by 7, which just creates a 1 there. Minus 4, 0, 0, 1, 2, 1. Now, I mean, here we already had that staircase shape. There's not a whole lot to do for it. But now we have that staircase shape, and that's a 1. So now we can use that to make a 0 above it. Row 1 becomes row 1 plus 3 row 2. Remember, using this row to make a 0. So 0 added to that stays the same. 0 added to that stays the same. 3 times 1 added to that becomes a 0. 3 times 2 is 6. Added to minus 3 is 3. And then 3 times 1 is 3. Added to minus 4 is minus 1. And now we have that nice staircase shape. And there's zeros above and below those numbers, right? So what do? This, right? We say, hey, this is a system of equations. So this means x1 minus 2x2, that's 0 plus 3x4 equals minus 1. This is a 0, that's a 0. x3 plus 2x4 equals 1. So now we look at this, we have some extra variables, ultimately, right? It looks like there's some fuzziness here, right? We didn't get a specific answer. And that matches up with the situations I've said we can be in. Either we have a unique solution, just one, like this, or we have infinitely many of them. How can we possibly have infinitely many of them? We must be given a choice at some point to pick a number to be anything we want, right? And that's what happens here. So this, infinite solutions. So we can actually tell that we're going to have infinitely many of them in advance. If we look here, remember all of these stand in for the variables in equations, right? These are the things that go in front of x1, the things in front of x2, the things in front of x3, and the things in front of x4, right? If we've got a 1 there, then we're in good shape, right? This is what's called a leading variable because this corresponds to a leading entry. So that corresponds to this variable and this variable. But what about the other ones? What about x2 and x4? If we look, there's no 1 in their column, right? They're just kind of, they appear all over, but there's no leading 1 that we could use to eliminate stuff up or down, right? So these are what are called free variables. x2 and x4 are free. What does that mean? It means we can choose them to be whatever we want, right? So you could say x2 is 3 and x4 is 1. What happens? Well, when you plug those in, you'll get x1 equals something and x3 equals something else. So then you'll have an answer for all of them, right? So what we do is we solve, or I could just say move free variables to the other side. So in this, got x1 minus 2x2 plus 3x4 equals minus 1. And we got x3 plus 2x4 equals 1. So what I'm saying is we're going to take this, and we're going to take this, and move them to the other side of their equations, right? So it'll be x1 equals, and now you can kind of see what I mean here, right? x1 equals something in terms of x2 and x4. Move this over, 2x2 minus 3x4 minus 1. x3 is 1 minus 2x4. Doesn't matter which order you write them in, it's fine, it's just an equation. So what I'm saying is x2 is free. x4 is free. You can choose it to be whatever you want. It's not uncommon for textbooks, if it helps people think about it, to replace this with a letter, right? To indicate it is a parameter. So this is, I'm going to say this is optional. If you just wrote this, it's fine. I would give it like that would be fine. This is sort of going above and beyond. What you could do is you could say x2 is equal to, I don't know, pick a letter, S, and x4 is t, right? That's physics parameters, right? It's parameters. And then you just replace the variables to make it very, very clear that we have the ability to choose them. x3, so 1 minus 2t. Right, so then you just know, okay, if I pick s to be 1 and t to be 3, then it completely tells me everything I need to know, right? I would know what this is, I would know what this is, I plug them into here, and I know what I need now, right? So I would say getting comfortable with systems that have free parameters or free variables is, it takes some time because there's this extra manipulation here. But in terms of, you know, look, your students care about grades. I get it. In terms of how much of the question have you done, if you got to here, which is the same as the other one that has a unique solution, you're getting like at least 4 out of 5, probably 4.5 out of 5. Like honestly, it's like one extra step. And if you're like, I didn't get that step, I'd be like, okay, that's fine. This is most of the work, right? So, and even if this is 4.5 out of 5, then doing this and being like, I didn't get that part is 4 out of 5, right? Like it's most of the work is doing this stuff. And then now it's just reinterpreting it, right? So that's, I just want to make that clear that if you're looking at this specific step and you're like, oh, it's still manipulating equations, I don't like it. Well, that's okay. If you get it wrong, it's not going to be that huge, right? So, okay, now we've done 2 situations. Unique solution, infinite solutions. There's one more, but fortunately, this one stands out like a sore thumb. And it's the no solution situation. Again, can I I need the space. I wish I had the big whiteboard still, but I don't. So I have to do that.
Just draw on the TVs.
So I'm actually thinking about doing that. It's a bit late now, but like I am considering it. Maybe on Wednesday I'll have a tree. They have a document camera in here? They do. So actually, again, it's late for me to be trying this, but I think I'll try it because I get it. I am a brick wall. It's hard to see the stuff past me. So what I can do is I can use that document camera and sit at that desk and point it at a sheet of paper, which just pretends to be a whiteboard, and then I just put it on the screens. Right? Genius. So screw it, I'll try that. I mean, if I don't have the space on the whiteboard, I might as well just do something like that, right? So I'll try that on Wednesday and we'll see how it goes. Anyway, let's solve this. 2x1 plus 3x2 equals minus 1, minus 4x1 minus 8x2 equal to 3. All right, so it's a system. That's nice. Okay, so we, again, same process. We go ahead and we say, all right, write down the matrix. That's always going to be the first step. So we go ahead and we read this off. 1, 2, 0. 2, 3, minus 1. Minus 4, minus 8, 3. And now we just do our thing. So we already have a 1 at the top left. Awesome. We don't have to do anything to put it there. So now we just want to kill the stuff below. So that's going to be row 2 comes row 2 minus 2 row 1. And row 3 is row 3 plus 4 row 1. So we're just getting rid of those entries. Bless you. So, well, I know this is a 0 and this is a 0. I did that on purpose. So what about the other ones? 3 minus 2 times 2. So 3 minus 4 becomes minus 1. That's minus 1 minus 0. Minus 8 plus 4 times 2 is 8. This is a 0. 0 to that is 3. Okay, so this is what I mean by it kind of stands out to you like a sore thumb, because at every step of every single one of these, it still represents a system of equations, right? So let's take a look at this. We could keep going, right? We could create a 1 here and then keep going. But what does this mean? This means x1 plus 2x2 equals 0, minus x2 equals minus 1, 0 equals 3. That's nonsense, right? 0 equals 3, right? Really, it's 0x1 plus 0x2 equals 3. Nothing we could choose will make that true. Nothing at all, right? So we say this has no solutions. We don't need to keep going, right? This is already impossible. No solutions. And when I say it stands out to you like a sore thumb, what do I mean by that? Well, we got the staircase shape. To the left here of this line is variables. To the right is not variables. So if you ever have the leftmost non-zero entry being in this part, stop. You already have no solutions, right? Because what that would mean is you'd have, you got a bunch of stuff here, but you've got, a bunch of zeros. Who cares how many zeros? And then you have some number, right? And that just automatically means it's going to be 0 equals number, which you can't do. So you just stop as soon as you see this. I mean, some students will just keep going, and it's like, that's fine. But as soon as you get a shape that looks like this, where you've got to jump down on the staircase shape past this line, you don't need to keep going, right? So stop. as soon as you notice. And that covers all three situations. So we did unique solution, infinite solutions, no solutions. And I'm going to give you lots of practice on this. Don't worry about that. But you can now solve any system of equations. Like it doesn't change, right? It's the same no matter what number of variables of equations we pick. You just go through the motions. And yeah, of course, if I gave you like an equation with 10 variables and 15 equations, you would be like, Travis, I hate you. So I'm not going to do that. They'll stick to like simple stuff like this. But I mean, maybe on the programming assignment, we have the power to do something like that, right? To say like, okay, whatever. But I think I already posted it, and I don't think it has anything like that. So, oh well. But yes, if it's not clear, I have nothing more. So we're done a few minutes early. So next class will be sort of the quiz again. It's gonna be like just do one of these basically, right? I'm gonna maybe I'll even do one on the board to get us warmed up. I'll be like let's do one so that we're refreshed, and then you're gonna go ahead and do it, get some practice on it, and then we're gonna also talk about. So for matrices, we've introduced the concept of them, but just like everything else in the course, where we said, okay, we've got these logical operators and truth tables. What can we do to them? We've got these sets. What can we do to them? So we've got these matrices. What can we do to them? So we're going to talk about that. And matrix multiplication is, yeah, it's not. It's not actually that bad to do because there's like a methodical process where you use your fingers. That's fine, but it is not well behaved. It is not good in the mathematical sense. So we're going to talk about that. And all this time where I've been like, hey, I write down that commutative thing and I write down the associative thing, and you're like, yeah, Travis, no shit, right? That's true for everything. Not anymore. This is going to be one that violates that. So we'll do lots of examples. And matrix multiplication behaves very weird. But that's for Wednesday. I'll get us warmed up to that, and then we'll do the quiz. Yep. Just from the sheer I don't want you to have to write too much, because here's the secret: if I have to make you write too much, I have to make the solution, which means I also have to write that amount. So there's some